Okay, so what I want to talk to you for just a minute is the probability distributions that we talked about yesterday in class, as well as binomial distributions, which are a type of probability distribution. So feel free to fast forward through what you need or through what you don't need, and to pause or rewind as we hit things maybe that you didn't quite understand, because I know that the lesson on this was a bit rushed. So probability distributions, what they do is they represent all possible scenarios, let's say, of something that I want to represent. And remember, in a probability distribution, I've got a couple of requirements. All my probabilities must be positive, and they must all sum to 1 or 100%. Okay? I'll have a random variable x, and then I'll have the probability of that random variable occurring as one of the rows in my table here. So let's say, for instance, I looked at your last test scores, okay? And this is just some random data that I'm going to make up. It's not at all true, but let's say I looked at it, and of those, there were 7 A's. Let's say there were 4 B's, 10 C's, 3 D's, and 2 F's. So what I want to look is I want to look at what's the probability that a student made a C, or what's the probability that a student made a D, or what's the highest probable score on the test. And we're not looking at exact numbers, we're just letting this random variable be the letter grade that associated. Okay, so first thing I want to do is sum up these. This would be 11, 21, 24, 26. Okay, so I've got 26 total students here in this fictitious set of data, and I want to find the probability of each letter grade. Okay, so my random variable is going to be the grade itself. So you could make an A, a B, a C, a D, or an F. Okay, so what is the probability that you make an A? Well, if I come over here, 7 students made an A out of 26, right? How about a B? That would be 4 out of 26. Moving on to C, D, and of course F. Okay, and I'm not simplifying these fractions any just yet, because I really want you to see that it does, in fact, all of these probabilities are positive. That's good. And additionally, if I added together, 7 plus 4 is 11, plus 10 is 21, plus 3 is 24, plus 2 is 26, I would get 26 over 26, which we know to be 1. So it does satisfy those requirements of a probability distribution. Now, what I also want to do is take just a second to graph these. And so I'm going to do a little histogram here. My x-axis is my random variable axis, okay, and I'm going to let my probability be on the vertical axis here so that it's a little easier to graph. Okay, so let's see, I go from 2 up to 10, 2, 3, 4, so I'll just let each line be 2, 4, 6, 8, 6 there, and 10. And of course, let's see, I'm going to have A, B, C, D, and F as my random variables here. And so let's just graph. For A, 7 out of 26, so I'll come up to 7. B is going to be 4. C, I didn't make my first bar there quite wide enough, but that's okay. C will go up to 10. D will be 3. And F is 2. Okay, so as you look, you can tell a lot of things by looking at the histogram, and that's why they're really convenient and really handy. Looking here, you can tell that the most probable grade is a C, right? So the most probable is a C, which we would expect if this was really a true set of data for the test, right there in the middle. Little more A's than there are B's, which is, that's pretty good. And you can also look here and tell what's your probability. What if I wanted to know what's the probability of passing, maybe? Okay, so if we're looking at a D or better, and notice I used the word or, and remember when we're talking about or, we're talking about adding, right? So what's the probability of making an A or B or C or D? Well, the probability of making an A is 7 out of 26. Or means add. 4 out of 26 for the B. Again, add. The C is 10 out of 26. Add. And the D is 3 out of 26. So the probability of passing the test would be 24 out of 26. And let's see, that would be approximately 92%. So there's a 92% chance that if you take that test, that you pass that test, right? So we can analyze this a lot. All right, so that's probability distributions. Let me show you also. Here I said the probability of passing. This may be written as the probability that X is greater than or equal to maybe a D, or if it was a value, it might be written that way. But this is just saying the probability that X is bigger than this value. And I say bigger, I use that term kind of loosely here because we're talking about letter grades, but you understand what I'm saying, that it's greater than a certain value. Or maybe I said, using this data, what's the probability that X is a B? So what's the probability that you make a B? Well, if you look at your chart, the probability that you make a B is 4 out of 26, right? Which would roughly be 15%. Okay? All right, so that is normal probability distributions. Now, let's say that I'm talking about binomial. So we talked a little bit about binomial, and we talked about how binomial has some stipulations, right? Binomial means that there are two possible outcomes, okay? There's a success outcome, there's a failure, and it doesn't necessarily have to be success or fail. It can be yes or no, true or false, flipping a coin, heads or tails. It is or it isn't, okay? So two outcomes. The events that are occurring within the binomial distribution are independent of each other, meaning they don't impact each other. If you flip a coin 100 times, it doesn't matter what you flip on the 50th flip. It's not going to impact the 51st flip. If you're randomly guessing on multiple choice questions, it's not going to matter what you randomly guess for question number 10 as far as what you randomly guess for number 11 if they're truly random. Okay, so each one's not impacting the other one. They're independent of each other. So if this is true, we have a little formula for binomial. And let me lay it out for you here. It's n choose k times p to the k times 1 minus p to the n minus k. All right, so a little bit different than what you're used to. N. Okay, n is my total number of trials, we'll say, or whatever it is that we're looking at. If I'm talking about a 50 question test, then my n would be 50. If I'm talking about 100 flips of the coin, my N would be 100. Okay, so it's the total trials, it's the number of trials that I'm looking at. K is going to be my number of successes that I want. Okay, so I want to know if I flip it 100 times, what's the probability that I get exactly 10 heads? So my K there would be 10. P is my probability of success. If I'm talking about flipping a coin, the probability of getting a heads is, of course, 50% or 0.5. The probability of guessing right on a multiple choice question that has 4 choices would be 0.25. So that's my P there, okay? And then everything else kind of just follows suit. It's the same variables over and over. 1 minus P, that's going to be really what you're finding is your probability of failure. If P is the probability of success, then 1 minus P is your probability of failure. In other words, I've got these answer choices, right? A, B, C, and D. If the probability of picking the right one is 0.25, so my probability of success is 0.25, then my probability of failure or my probability of not picking the right one, well, then I've got a 75% chance, right? Because there's 3 options left. So what that is 1 minus the probability of success. So what I can do is I can use this kind of information and I can set up a whole binomial probability distribution, okay, based on certain scenarios. So let's do one. Let's say you have, and we'll do this easy, let's say that we have a multiple choice test that has, we'll do 10 questions. It'll be kind of long, but we can do it. 10 questions, right? Each of those 10 questions, and I'm going to even change this up, I'm going to say each of those 10 questions have 5 answer choices, A through E. Okay. So what I want to do is I want to set up a binomial probability distribution of the number that you can get right. All right, so let's think this through. X is going to be my random variable, and my probability of X here. So X is going to be my number right. Okay, that's what I'm going to look at. So if there's 10 questions, I could get none of them right. 1, 2, 3, 4, 5, all the way to 10, right? It's a big distribution. But we can use this distribution to answer a lot of questions. Okay, so my first question is, what's the probability that you take this 10 question test, you randomly guess on the whole thing, and you get no questions right at all? Okay, well, what that's going to be, remember my formula here, my NCK, right? 10 questions, choose none. My probability here, this time I've got 5 answer choices. So my P in this case is going to be 0.20, right? 20% chance of choosing the right one here rather than 25% chance. So my odds are a little bit lower, but that's okay. So 0.2, I'm raising that to the 0. Then I'm going to do 1 minus 0.2, and I'm going to raise that to the 10th. Okay, so this is really 10 choose 0, 0.2 to the 0, and 0.8 to the 10th. Okay, so let's see what we get. So if you randomly guess on the whole test here, we've got and we'll put this in parentheses, 10, math over to probability, 10, choose 0. I'm going to multiply that by 0.2, 0.2 to the 0, times, and remember we said that was 0.8 to the 10th. 0.107. So I have about, and understand what this is saying. This is saying that you randomly guess on all 10 questions and you don't get any of them right. So this is about 0.107, which is about 10.7%, right? Little over 10% chance of getting none of them right. All right, let's move on. So for 1, 10, choose 1, 0.2 this time to the 1. I'm going to go ahead and put the 0.8 here, and this is going to be 9 because it's 10 minus 1, right? So when I do this one, and if you don't know this little trick with your calculator, I'm going to show you. If you do second enter, it'll pull up what you just typed. I'm going to change this to 10, choose 1. I'm going to change this to 1, and I'm going to change the last one here to 9.268. So 0.268. Better chance. That's getting a little better, right? So you got a close to 27% chance of randomly guessing one of them right. All right, let's do the next. 10, choose 2. 0.2, 0.8, and so I'm going to come to my calculator again, same thing. 10, choose 2, 0.2 to the second, 0.8 to the 8th, 0.302 we'll say. We'll round it out 3 places. Oh, getting a little better. So you got a 30% chance of making a 20, right? Since there's 10 questions. Let's move on. Let's do number 3. 3.2 to the 3rd. Again, if you understand and you want to fast forward through, be my guest and meet us back at the end. But we'll keep trudging through here. This is a 3, a 3. This one will go down to a 7. 0.201. Uh-oh. Looks like I peaked here and I'm coming back down. All right, 10, choose 4. Let's do 4, 4, 6.088. Yep, looks like I'm coming back down. All right, let's do 5 then. Five, and 5.026. Oh yeah, it's starting to get smaller here, right? Let's do 10, choose 6. 0.2 to the 6, 0.8 to the 4. So I have 10, choose 6, 6 and 4, 0.006. Let's do 7. So this would be 7, 7 and 3. Oh, so here we have scientific notation that tells me to move the decimal over left 4 times. So it's going to be 0.000, and we'll round that 7 to an 8. We're getting really close to 0 here. 10, choose 8. Which makes sense, because what's the chances that you would randomly guess 7 questions out of 10 right? Just guessing on a multiple choice test, right? I'm getting pretty close. All right, so I'm going to go 8, 8, and 2. Now I got 5 zeros, right? 1, 2, 3, actually 5 times to the left, excuse me. 4, and then I have a 7. 9. 9, 9, and 1. 6. 1, 2, 3, 4, 5, 6. And then 10. So this is the probability that you randomly guess every single problem right on the test. That clearly you didn't study for, right? And get them all right. 1, 2, 3, 4, 5, 6. Reminds me of that movie Dumb and Dumber where Jim Carrey says, so you're telling me there's a chance, but my gracious, it is terribly small. What a terrible chance. So if you randomly guess 10 questions, here are my odds, right? If I were to add all these together and didn't have any rounding issues, they would add to 1. Everything's positive. This is my binomial distribution. So let me ask you a couple questions. Let's do a little analysis on it. What's the probability that let's say you pass, that x is greater than or equal to, what you would have to get a 60 to pass, so 6 or better, greater than or equal to 6, right? So greater than or equal to 6, that would mean you would need to make a 6, or 7, or 8, or 9, or 10, which of course means I'm adding, right? Because that's what or means in probability. So I need to add from 6 up to 10. So 6, 7, 8, 9, and 10. 0.00, I'm going to say approximately 0.0069, and I took this out that many places because I want you to see that what this essentially is a 0.69% chance of randomly guessing enough right to actually pass the test on a 10-question test. Remember, 5 answer choices, so the odds are a little bit worse than what they were. The most probable here, if I needed to know the most probable, of course, would be 2. So the most likely grade that you're going to make, randomly guessing, is a 20. Okay? But notice how we added here. So the probability that x is greater than or equal to 6, then we added from 6 and above. If the probability that you make at most a 30, you would say at most would be from there and below, so you would add all of these together. Okay, I hope that makes sense to you as far as how to calculate. Now, you will encounter some problems, and this is what I really wanted to talk to you about, because students always, for some reason, get hung up. You're going to encounter some problems that it's not going to be quite as straightforward. They may just give you a P, a K, and say find the probability of yada yada yada. So let's look at a couple of those also. Let's say I told you that I had a binomial distribution. Okay, so anytime you see the word binomial, you're already keyed in to the little formula NCK P to the K 1 minus p to the n minus k. Okay, this little piece is all my leftovers, right? That's what's left over of my p. That's what's left over of my n after I take the k away. So let's say I have a binomial situation set up, and the probability of success, or my p, is 0.37. Okay, and my number of trials is 4. And I want to know what's the probability that x is greater than or equal to 3. Okay. What that means is I'm looking for, I need to do the probability of 3, and I need to do the probability of 4, and I need to add these two probabilities together, because greater than or equal to 3 would be 3 or 4. Now I'm only going up to 4, right? I could set up a whole distribution for this, but it's not asking me. It's only asking me the probability that x is greater than or equal to 3. So here, the probability that it's 3, of course, n is 4, so it would be 4 choose 3 times, my probability is 0.37 to the third. If this is 0.37, then 1 minus 0.37 would be 0.63 to the first, because I subtract the 3 and the 4. Okay, but to that I'm going to have to add the probability of 4, which again, plug in that formula, 4 choose 4, p is still 0.37, this time it's to the fourth, and 1 minus p would be 0.63, of course to the 0 power. Okay, and then I could add those values together. So if I had 4 choose 3 times 0.37 to the third times 0.63 to the first, okay, 0.127 approximately, but then to that I'm going to need to add, I'm going to call up that last entry again, so I got 4 choose 4, I got this to 4, and I got this to 0, 0.018. Okay, I'm going to take that, and to it I'm going to add the 0.127645556, and I get 0.146 approximately. So I really want you to see that it doesn't matter if I've got a situation laid out and defined, okay, like I did with my whole test, with my multiple choice test, right? It's laid out. It's a nice little word problem for me to look at, to analyze, and it's cool. Or maybe I'm just given the p and the n, and I'm asked to do a probability distribution from that. And what you could now understand, I could do my x, I could do my p of x. Okay, if n is 4, that means my x could be 0, 1, 2, 3, or 4, and I'd have to use this same formula to find each particular value, right? We've already done it for 3, it was 0.127, and we did it for 4, it was 0.018, and you could go through and do these other 3, right? So it really doesn't matter if you're given a situation to set up or if you're just given some information. One more that comes up a lot is a coin toss. And I know I've been talking a long time, and I apologize, but I just want to make sure you got it, okay? Let's say I flip a coin. We keep saying 100, so we'll say 100 times. Okay? What's the probability that flipping that coin 100 times, you get exactly 70 heads when you flip it? Okay? So we need to define a couple things. We need our N, we need our K, we need our P, right? If I'm flipping it 100 times, then my N is 100. My number of successes that I want, 70, right? And my probability of success, well, if you flip a coin, what's the probability that you get heads? It's a 50-50 chance, right? So 50%, 0.5. All right, so I'm going to plug in my little formula. Remember, n, choose k, p to the k, q to the n minus k. All right, so I have 100, choose 70, 0.5 to the 70. Q, I put Q, I'm sorry, I'm so used to doing this in problem stats. This is that Q is 1 minus P, that's the same thing. 0.5, and then leftover is 30. Okay. All right, so I end up with 100, choose 70 times 0.5 to the 70 times 0.5 to the 30. Ooh, pretty small, right? Let's see, approximately 1, 2, 3, 4. Oh, not 5. 4. This is a 2, 3, 1, 7. Okay, that's your odds of flipping exactly 70. Now understand, I'm not saying 70 or more, 70 or less, exactly 70. Flipping it 100 times and getting exactly 70, so there's not a very good chance. Your most probable here would be 50%, since it's a 50-50 chance here of getting either one. Okay, so I hope this clears up your distributions, your probability distributions. Remember, even for all of these, we can still do the histograms that go along with them. I probably should have showed you on this other, but here I still could have done the histogram. It goes, the highest is 0.3, right? And I just label that vertical axis with the different probabilities, and it's easy to see there. Okay, I think you should be good now. You've got your assignments. If you need me, you can get me. But I think you should be good on probability distributions now.